In this lecture, we're going to dive into an exciting and powerful concept in Python, operator overloading. This is what allows Python classes to redefine the behavior of standard operators like plus, minus, and equals. You might have noticed that Python already lets us add numbers, compare strings, and multiply lists, but what if we want to make our custom objects behave this way too? That's where operator overloading comes in. We'll start with the basics of operator overloading and then dive into specific cases like addition using the add method and subtraction with the sub method. Afterward, we'll see how to handle multiplication by implementing the mul method. We'll also cover comparisons, including checking equality with the EQ method and comparing objects using the LT method. To tie it all together, we'll use a practical example, a vector class representing points in 3D space with x, y, and z coordinates. We'll implement operator overloading for addition, subtraction, scalar multiplication, and comparisons. So by the end of this lecture, we'll understand how to overload operators to work with our custom objects. Let's start with a quick introduction to the idea. Operator overloading allows us to redefine how operators work for user-defined objects. Python already knows what to do when we use plus between numbers, but when it comes to custom objects like our vector class, we need to tell Python what plus, minus, or equals should do. Python offers special methods, also known as dunder methods, such as add, sub, and EQ, which we can implement in our classes to define how certain operations behave. These methods guide Python on what to do when operators are used with our custom objects. Now, let's start implementing our vector class to see how this works in practice. For that, we'll create a new Python file and name it vector.py. In the file, we'll define our vector class that represents a 3D vector with x, y, and z components. Our constructor takes 3 arguments as the coordinates of our vector. First of all, let's override the str method to provide a readable string representation of our vector. This method is automatically called when we print the object or use str on it. It returns the vector's components in a formatted string. Now let's create 2 instances of our vector class. After creating these vectors, we'll use print statements to display them. Since we've overridden the str method, Python will automatically format the vector into the XYZ style when we print it. Let's run the script and verify it. As a result, we'll see the formatted output showing the coordinates of each vector. Now, let's add support for adding 2 vectors together. We know that mathematically, vector addition is component-wise. To do that, we define the add method. It's what Python will call when we use the plus operator between 2 vectors. Here, the parameters self and other represent 2 vector objects that we want to add together. Self refers to the current instance of the class and represents the vector object on the left side of the plus operator. Other refers to the vector object that we're adding to self, meaning the vector on the right side of the plus operator. Inside the method, we add the x, y, and z components of both vectors and return a new vector object with the resulting coordinates. This allows us to perform component-wise addition of the 2 vectors. Next, we'll add the 2 vectors, v1 and v2, using the plus operator. The result will be a new vector, which we'll store in v3. Thanks to the add method we defined earlier, Python knows how to handle this operation for our vector objects. When we print v3, Python will once again call the str method to format the output, showing the coordinates of the new vector. If we run the code at this point, we'll see the result of the addition. Next, we want to implement subtraction in the same way as addition. Vector subtraction is also component-wise. Let's define the sub method. When we subtract two vectors, we'll get a new vector representing the difference between their components. Let's see this in action by subtracting v2 from v1. After running this, we should see v4 as the result of vector subtraction. Now, what about multiplying a vector by a scalar? We might want to multiply each component of a vector by a constant. For this, we'll overload the mul method. This will allow us to multiply a vector by a scalar. Let's try it by multiplying v1 by 3 and assigning the result to v5. If we execute this code, we'll observe the result of such a scalar multiplication. Note that the mul method only handles multiplication when the vector is on the left side of the operator, like v1 times 3. However, if we try to multiply the scalar from the left side, such as 3 times v1, Python won't automatically know how to handle it. To fix this, we need to implement the rmul method, which allows us to define the behavior for scalar multiplication when the scalar comes first. This way, our vector class will support multiplication from either side, which ensures both v1 times 3 and 3 times v1 work correctly. Now, let's add the rmul method to our vector class too. Note that inside rmul, we call the mul method to reuse the logic for scalar multiplication. Next, we'll test our newly added rmul method by multiplying the scalar 3 by the vector v1. Since the scalar is on the left side, Python will now call the rmul method to handle this operation. If we run the script again, we'll see exactly the same result. This ensures that scalar multiplication works seamlessly from both directions. Let's move on to comparisons. First, we'll define the EQ method to check if two vectors are equal. We'll use a tolerance value, say 0.0001, because floating point calculations can be tricky, and exact comparisons might not always work. Let's add our tolerance as a class variable. This will be used for comparisons, like when checking if two vectors are equal. By defining it at the class level, all instances of the vector class will share the same tolerance value. This makes it easy to adjust the precision of equality checks without needing to modify each instance individually. Let's now go ahead and add the EQ method to our vector class. This method will determine if two vectors are equal by comparing their x, y, and z components within the tolerance we defined earlier. The condition C1 checks if the difference between the x values of self and other is smaller than our total value. Similarly, C2 and C3 do the same for the y and z components. If all three conditions C1, C2, and C3 are true, then the two vectors are considered equal and the method returns true. Otherwise, it returns false. Note that we could also access total using vector total instead of self-total, because it's a class variable shared by all instances and can be accessed directly from the class. Using vector total makes it clear that we're referring to a class-level attribute, rather than something specific to an individual instance. However, using self-total works too, as Python will automatically look for the class variable if it's not found in the instance. Now we can use the overloaded equality operator to check if v1 and v2 are equal. Let's run the code and verify if it works as expected. It returns false, indicating that the vectors are not equal. Now, as another example, let's move on to the less than comparison check using the LT method. This method is intended to compare two vectors based on their magnitudes, or lengths. The idea is to determine if one vector is shorter than another. First, we define a helper method called magnitude, which calculates the length of the vector using the Pythagorean theorem. It sums the squares of the x, y, and z components, then takes the square root to get the magnitude. Then, the LT method compares the magnitudes of self and other. If the magnitude of self is less than that of other, it returns true, otherwise it returns false. This allows us to use the less than operator to compare vectors by their length. Now let's check if v1 is shorter than v2 using the less than operator. When we run this, we'll see that the result of the comparison check is true. To summarize, in this lecture, we explored how to overload operators in Python using our custom vector class. We explored how to redefine addition and subtraction between vectors. We also covered scalar multiplication from both sides. Finally, we learned how to handle comparisons, such as testing equality and less than operations between vectors. This is a very powerful feature that allows us to extend Python's behavior to work naturally with user-defined objects, making our code more intuitive and flexible.